All right, here we go. Today we are going to talk about limits at positive or negative infinity. So write down that title 1.6 notes, limits at plus or minus infinity. Okay, and then we're gonna look through 3 possibilities for limits at plus or minus infinity before we get kind of started with our notes. You do not have to draw these, but it might be worth drawing, honestly. I would encourage you all to draw these. So really quick, if we're looking at x approaching positive or negative infinity, we have 3 options for our limit. So you can see here, we are looking at x approaching plus or minus infinity, and we're going to go over our 3 options. So first, let's just use this graph, and we'll actually write what the limit is. So the limit as x approaches positive infinity of f of x, this y value on this graph is going up forever. So the limit, the y value, is going to positive infinity. All right, and then if we go down here, the limit as x approaches negative infinity of f of x, that function is pointing down forever. The y value is going to eventually get to negative infinity. So our first option for limits approaching plus or minus infinity of f of x is plus or minus infinity. Okay, and like I said, you could sketch a rough graph really quick to just give yourself a visual. So now we're on to our second option for limits approaching plus or minus infinity. And let's look at the limit as x approaches positive infinity of this function, f of x. So if we're approaching positive infinity, that's x going to the right, because positive infinity, that's an 8. Positive infinity is this way, right? What y value is our function getting closer and closer to? It's getting closer to 0. For 1 over x, we're getting closer to 0. And we're not going to touch 0. And then what about the limit? Oh, sorry, 0. What about the limit as x approaches negative infinity of f of x? So as x goes this way forever, negative infinity, what is our y value getting closer to? Again, our y value is getting closer to 0. So another option for limits approaching plus or minus infinity is 0. All right, and now let's go to our last option, the limit of x approaching plus or minus infinity of this function. So let's just look at the right limit at first. The limit as x approaches positive infinity, so this way. Where is our function getting closer to? This value, this y value of 1. We have to stop at that y value, right? So for this function, our limit approaches 1 on the right. And then on the far left, as x goes to negative infinity, the function, again, is getting closer and closer to that asymptote, but is not allowed to touch it because that's the definition of an asymptote. So our limit as x approaches negative infinity is also 1. So instead of writing 1 up here, instead of writing 1 for our third option, we're going to write just some number. Some number. So just as a reminder, or make sure you have all these possibilities. There are 3 possibilities for limits when x approaches positive or negative infinity. Either the limit will equal plus or minus infinity, or the limit will equal 0, or the limit will equal just some number. Okay, cool. Now let's talk about how we know which one of the 3 happens. But first, what do you notice about the example where the limit as x approaches positive, negative infinity equals some number? So let's go back to that one. That's this example. What do we notice about this example? What do we have? We talked about it already. What do we have right here? This is a horizontal asymptote. So we have a horizontal asymptote there. So just like this graph has 2 horizontal asymptotes, and your limit actually equals the horizontal asymptote, depending on if you're approaching positive infinity or negative infinity. Okay, so we're going to write a little note to ourselves. If we're right here, if the limit as x approaches positive or negative infinity of f of x equals some number, your function has a horizontal asymptote. a horizontal asymptote at that number. Okay, so anytime you just get like some number from a limit as x approaches positive, negative, infinity, you get a horizontal asymptote at that number. And we can actually use limits approaching infinity to find horizontal asymptotes. We will do this later, like later today. Okay, really quick, we're going to need to talk about the reciprocal of 0 and infinity, just so we can kind of visualize these limits. So what is a reciprocal? A reciprocal, you should write this down. A reciprocal is the flip of a fraction. It's the flip of a fraction. Or you can think of 1 over like whatever you started with. So put it under 1. You could also think of put it under 1, whatever you started with. Okay, so now let's talk about what is the reciprocal of 0. So I already filled out this table, but we're going to look at this table below to find the reciprocal of 0. So we put 1 over 0, right? We're plugging in numbers that are getting closer and closer and closer to 0. But remember, we're not allowed to divide by 0, so we can't actually plug in 0. So we're just going to like think about the limit. So right here in this table, we're finding the limit as x approaches 0. It's getting closer to 0 of 1 over x, but it can't actually equal 0. Okay, and in the box, I want you to tell me, what does it look like this limit is approaching? What does it look like this limit's getting closer to? As we get closer to 0 in our x values, what is the limit getting closer to? What is the y value approaching? Okay, so you should have noticed that this y value is going up forever. It's getting bigger and bigger and bigger, which means that it's approaching infinity. This y value is approaching infinity. So we're going to say 1 over 0 goes to, this arrow is goes to, because we can't equal infinity. So 1 over 0 goes to infinity. And we're actually going to put plus or minus here because we could have just put a negative there as well, right? And then all these would be negative and it would get closer to infinity. Okay, and then let's continue. What about if x is approaching infinity? So the limit as x approaches infinity of 1 over x. So if I keep plugging in bigger and bigger and bigger and bigger and bigger numbers for the x value in this 1 over x function, I'm going to get smaller and smaller and smaller and smaller and smaller numbers. What are these numbers getting closer to? These y values, what are they getting closer to? What is this limit approaching? Go ahead and put that in the box. Okay, because they're getting smaller and smaller, and you have more and more zeros after the decimal, 1 over infinity is getting closer to, or it is going to, 0. 1 over infinity goes to 0. Okay, so a key idea. Plus or minus 1 over 0, you need to make sure you have this in your notes. Plus or minus 1 over 0 goes to plus or minus infinity. And that's like, it's kind of like a limit. Make sure that you know this arrow means goes to. That is not the same as equals. Okay, 1 over plus or minus infinity goes to 0. So we need to know those two things to kind of understand the limits today. All right, let's keep going. Limits as x approaches plus or minus infinity. How to think about functions when we're looking at limits approaching plus or minus infinity. All right, if we plug infinity into the numerator or denominator of a rational, so now we're talking about if we have rational functions, fraction functions, so they look something like this, we will get a fraction that looks like one of two things. All right, one, you're going to get ginormous over small, something giant over something small, or two, you're going to get something small over something ginormous. That's if we plug infinity into a rational function. Okay, so I want you to kind of like simplify this in your own words. You could just like, these are fractions. This means over, right? Ginormous over small, small over ginormous. Okay, and then for the sake of today, we're going to imagine that elephants are the same as plus or minus infinity, because elephants are ginormous, right? And so is plus or minus infinity. And then puppies are the same as 1. That's for today's lesson, because 1 is a very small number. All right, so let's move on. You're going to get either big over small or small over big. And let's see an example so that makes more sense. Okay, actually, let's really quick summarize that. So for the limit of f of x over g of x as x approaches positive or negative infinity, and I want you to write this down, all of this. This is important. We have the limit as x approaches positive or negative infinity of f of x over g of x will either equal elephant over puppy, or it'll equal puppy over elephant. Elephants are big, puppies are small, so that's the same as big over small, which is the same as plus or minus infinity over 1. And what would that simplify to? Anything over 1 is just itself. So that's the same as plus or minus infinity. So we have two options. Or for rational functions, your limit is going to be the same as puppy over elephant, which is small over big, which is 1 over infinity. And we just talked about how 1 over infinity goes to 0. So that is going to be 0. Okay, so make sure you have that down. And you might be like, what the heck are we even talking about? I'm going to show you with an example. It'll make more sense once we do our example. Okay, so now let's use this to solve some limits. Get these examples down. So consider the following 3 functions. And I want you to write down all 3 functions. Now for each function, does the numerator or denominator become big as x gets larger and larger? And we're going to imagine plugging in plus or minus infinity. Okay, so what I'm going to do here is I'm going to plug in plus or minus infinity on these 3 functions so that we can kind of imagine which one's getting bigger, the numerator or denominator. So let's just imagine, I'm going to say approximately equals, actually, you know what, we're not even writing what it equals. We're just imagining. So I'm just going to plug it in right here next to it. So we're imagining we plug in plus or minus infinity into the x. We would have that for f of x, right? Let's do the same thing for g of x. Always put parentheses around whatever you're plugging in. That's going to make sure you do your math correctly, your order of operations correctly. Okay, that would be what g of x equals, right? So I'm not saying these are that we're actually plugging in plus or minus infinity, but we're imagining what would happen if we did. And then h of x would be plus or minus infinity to the 7th over e to the plus or minus infinity. Okay, that's what these would look like. Oops. If we were to plug in plus or minus infinity, that's what these would look like. So now, let's think about which is getting bigger, the numerator or denominator. Which one's growing faster? So for f of x, what's growing here? What's getting giant? The denominator. Plus or minus infinity to the 10th, that's getting big. So we're going to call that the elephant. So we have 3 is a puppy, or small, over big. That's how I'm going to think of f of x, small over big. Okay, for g of x, we have plus or minus infinity squared on the top, plus 5. But this plus 5, is that going to be anything significant compared to infinity? No, that's so tiny compared to infinity. So we're not going to worry about this, the plus 5 or the plus 2. Which one's bigger, plus or minus infinity squared or plus or minus infinity? The squared, right? That's going to grow giant, way faster. So we actually, on g of x, we have big over small. The numerator is the elephant. Okay, and then for h of x, this one's kind of tricky. Which one's bigger, plus or minus infinity to the 7th or e to the plus or minus infinity? This one's tricky. E to the plus or minus infinity actually grows bigger. Anytime the infinity is in the exponent, that's going to be the giant one. So here we have small over big. Okay, why the heck are we doing this? Because we just decided, based on if you have big over small, small over big, we can figure out what the limit is as we approach plus or minus infinity. So big over small, your limit is going to be plus or minus infinity. And let's just like add a little note here, depending on the function. The sign, like the plus or minus, is depending on the function that you have. Okay, so now let's do an example, or like let's look at our example. F of x, we're taking the limit as x approaches infinity. We're taking the limit as x approaches infinity of a small over big. So let's go over here. That's almost, small over big is like the same as saying 1 over infinity, which is 0. So boom, that limit equals 0. Because if we plug in infinity, the 3 is insignificant. We basically get 1 over infinity because infinity to the 10th is infinity. Cool, so we're done with that limit. Now let's do it on g of x. Do the same thing, except here we're approaching negative infinity. So let's think about plugging in negative infinity. Now, I like to again, think about this 5 and this 2. These are so insignificant. If we plug in negative infinity and we plug in negative infinity here, these numbers are so tiny compared to these two numbers. So all we have to think about is which one is bigger, top or bottom. We already did that. Big over small, you're going to get big over small, you're going to get plus or minus infinity. Let's decide what the sign should be. This is negative infinity squared. That's going to be, the negative turns positive, so you get basically infinity over, this is negative infinity though, negative infinity, that's a negative, positive over negative, so this has to be negative infinity. And again, because it's big over small, it has to be plus or minus infinity, your limit. We just have to think about the sign. Okay, and then the last one we have is the limit as x approaches infinity of x to the 7th over e to the x. Again, this one is small over big, so this limit will equal 0. Those ones are easier, right, than the big over smalls. Okay, so what if the functions are the same size? Write this down. What if the functions are the same size? They're both elephants or both puppies. So how do we know, how do we know if they're the same size? First of all, we're going to look at the exponents. So look at, make a note of this, highest exponent to decide the size, S-I-Z, the size of the function. So if they're the same size, they have the same exponent. So we're going to go back to pre-calc. There was a trick for finding horizontal asymptotes. To find the horizontal asymptotes of a function, you're going to look at the exponents. Well, we're going to use this trick for limits too. What if those exponents are the same? If n equals m, n is this exponent, m is the exponent on the denominator. Then the horizontal asymptote is a over b. A is the coefficient, b is the coefficient. That's also true for limits. That's also true for limits. So if, I would write if same highest exponent, write this down. If the same highest exponent in numerator and denominator, then you're going to use the coefficients as the limit as x approaches plus or minus infinity. Okay, so here's an example of that. Write this example down. Find the limit as x approaches infinity of 3x to the 4th plus x plus 1 over 7x to the 4th minus 6x squared plus x. Okay, we can see that our exponent, our highest exponent on x, is 4 on the top and also 4 on the bottom. 4 equals 4. Those are the same highest exponents. So what are we going to use? Use the coefficients on that x. Your limit here equals 3/7. Now, sometimes you do have to pay attention to the sign, but we're plugging in positive infinity here. So if I plug in positive infinity to x to the fourth and positive infinity to this x to the fourth, the sign's not going to change. Again, these things, these other pieces are tiny compared to x to the fourth. So we can actually pretend that they don't exist. Don't worry about those. And then your limit will equal the coefficients because your exponent's the same. Okay, what if the AP exam asks us to find the horizontal asymptote? What if it says find the horizontal asymptote of a function using calculus? Okay, you need to know this. To find horizontal asymptotes, we can take the limit as x approaches positive infinity and x approaches negative infinity. This is our last thing, last example. So what are the equations of the horizontal asymptotes of this function? Y equals 2x over x squared minus 1, square root of x squared minus 1. Okay, here we go. To find the horizontal asymptotes, I'm going to take the limit as x approaches infinity of this function, and I'm going to take the limit as x approaches negative infinity of this function. And I intentionally did a rational or a radical function, one with a square root, because I wanted y'all to see how this is a little different. Okay, so as we take the limit, now we're going to do, I mean, you can do this every time if you want. You can do this every time if you want. But I really like to, I don't know. I like to do it this way. A lot of students like the puppy elephant thing, but I like to do it this way. So let's look at like how this works. The limit as x approaches infinity. We're going to imagine plugging in infinity. We cannot say equals and plug in infinity because you can't actually plug in infinity. So let's just imagine. I'm going to write it over here. 2 times infinity over square root of, actually really quick, before we imagine plugging in infinity, we have to get rid of things that don't matter. So what things are small? Really small, if you were to plug in infinity. This -1 is super small if we were to plug in infinity. This 2 also doesn't matter if we were to plug in infinity. So we could almost pretend that we're taking this limit. Limit as x approaches infinity of x over square root of x squared. Now, with square roots, you need to do something a little weird. You need to turn the square root into an absolute value. So we're going to say that's the same as limit as x approaches infinity of absolute value of x squared over x. Oh, wait, just kidding. The square disappears because what is the square root of x squared? That's just x. But because we had a square root, we need absolute value here. Okay, cool. Now we can imagine plugging in infinity. Infinity over infinity. What do you get? Same over same? +1. So this limit equals +1. Okay, cool. Now let's do the same thing for the limit as x approaches negative infinity. Again, the 2 is insignificant. Don't care about that. The 1 is tiny. Don't care about that. So we can pretend that we're taking the limit as x approaches negative infinity of, we still have x over absolute value of x. Because the square root, we turn into absolute value. Okay, equals. Now we can pretend, oh, let's not say equals because we're not allowed to plug in infinity technically. AP graders are really picky about that. Negative infinity over absolute value of negative infinity. Let's visualize this. What would that equal? Well, this guy turns positive on the bottom. So we could say like, oh, that turns into negative infinity over positive infinity. Negative over a positive equals -1. Okay. That limit is -1. So what are the equations of the horizontal asymptotes? Horizontal asymptotes always start with y equals +1 and y equals -1. The limit as x approaches infinity gives you and negative infinity gives you the horizontal asymptotes. All right. Good work today. I know that was a lot to take in. Now we're going to practice.